If I was to move on to number 5, it would look like this. So given the following system of equations, rewrite it in the form of ax equals b and determine L and U. So this is an LU factorization problem. So first writing it in the form of ax equals b, typically, depending on the type of system or the type of problem, the type of method you're using to solve, you may want x equals b. Sometimes you want your augmented matrix. For this, I really do want ax equals b because I want a and b to be separate. So a looks like this: 1, -2, 2, a -2, 6, -5, 4, a 3, 2. Here's one of my unknowns again, but that's okay. I'm not going to be concerned. I'm just going to move forward like normal. And then 3, x looks like this, and b looks like this. And then I need to find L and U. So here it says using L times U, which I'm going to solve it using my row operations and solving L times U. So if I know that L looks like this, this number here means that L32 equals 1. And then U should look like this. If I multiply these two matrices together, then I can set it equal to A. So when I multiply it together, I get U11. And it's just matrix multiplication. The notes has it as well. Okay, here we go. And I can just set that equal to A. And then I can just go about solving everything. So U11 equals 1, U12 equals -2, U13 equals 2. Then U11, which is 1, times L21 equals -2. So L21 equals -2. Then L21, which is -2, times U12, which is -2, plus U22 equals 6, or U22 ends up being 2. And then L21, which is -2, times U13, which is 2, plus U23 equals -5, or U23 equals -1. And then my last row, I have L31 times U11. U11 is 1. So I have L31 equals 4. L31 is 4. U12 is -2 plus U22, which I know what U22 is. It's 2, equals A32. So here is where I didn't really pay attention to A. It just happened to be there, and I just solved like normal. But here I can easily see that A32 should be -6. And then L31 is 4, U13 is 2, plus U23, which is -1, plus U33 equals 3. So my last one, U33, ends up being -4. So I have all of my pieces. So if I write them over here, L ends up looking like this. L21 is -2. L31 is 4. And then U can be constructed with my remaining numbers. 1, -2, 2. Then 0, U22 is 2, U23 is -1, and then 0, 0, -4. This is the first method I can use in order to find L and U. Another method I can use is using my row operations. So if that's easier for you, that's completely fine. Keep in mind that L32 equals 1. So I'm going to copy and paste A just over to this. Oop, shoot. Okay, go away. Copy and paste it Let's do it again. And I'll show you with row operations. Keep in mind that L32 equals 1, which means, we'll get to that in a minute. Okay, so my first row operation, row 2 equals row 2 plus some multiple of row 1. In this instance, that multiple is going to be 2 times row 1. So L21 should be -2. Remember, change the sign. And then row 3 equals row 3 plus some multiple of row 1. In this instance, it's going to be -4. So L31 equals +4. So change the sign. When I do that, I end up with this. So row 2 becomes 0 to -1, and row 3 becomes 0. Here I don't have a number, so I just end up with my equation that says A32 plus 8. And then this ends up being -5. So here my third row operation, R3 equals row 3 plus some multiple of row 2. Note L32 equals 1, which means this multiple is -1. When I do that, I should end up with 1, 2, 2, or 1, -2, 2, 0 to -1. And I want to end up with a 0 here. And then I end up with a -4, which means that A32 plus 8 minus 2 equals 0. So if I know I want this to be a 0, if I just plug it into my row operation, that means A32 ends up being -6. And there we go. That's another way where we can solve for A32. This ends up being my U, and then L ends up being constructed like normal. 1, 0, 0, -2, 1, 0, 4, 1, 1. So both of those methods you can use to find U and L. For this row operation method, it just takes a little bit more thinking in terms of what we want to end up with and how we can build our row operation. This one, there's more matrix math that you have to do up front. But we should always end up with the same answers for both L and U. And you can see that we got the same answers for L and U. Regardless of how you get to L and U, the next step, so we've done A, woohoo. The next step, it says solve the system using LU factorization. So we're gonna say Ly equals B, and then Ux equals Y. So if we get L, Y is our unknowns, and then we plug in B. B was originally 4, -10, -2. Solving for y1, up here we get y1 of 4. Here we have -2 times y1 plus y2 equals -10, or y2 equals -2. And this last equation tells us that we have 4 times y1 plus 1 times y2 plus y3 equals -2. Or y3 equals -16. Plug that into my second one. Ux equals y. So U looked like this. X is my unknowns. And then y. And then I just solve. So this one here tells me that -4 x3 equals -16, or x3 equals 4. Woohoo! If I plug that into this, I get 2 x2 minus 1 x3 equals -2, or x2 equals 1. Plug that in up here, I get x1 minus 2 times x2 plus 2 times x3 equals 4. Or x1 equals -2. Yay! If I want to check my answers in MATLAB, it would look something like this. So I found A to be -6. Yep, we found A to be -6. or the A32, whatever it is, A32. Plug in my A, plug in my B. I can't use, I can't use LU factorization. I can't use the LU function in MATLAB, but I can plug in what I got for L and what I got in for U. And I can say L times U to check to see if that matches what A is. So if A looks like this, L times U looks like this, I can check to see that they're the same. And then I can solve for Y using left division, solve for X using left division, and then solve my original system as well, just to confirm that, yep, I got my right Y values and I got my right X values, and that matches what my original system should result in. Okay, moving on to number 6, the last question. The last question is a little long, and it might take a while, but that's okay. Okay, so question 6 has to do with eigenvalues. Eigenvalues and eigenvectors. We are essentially talking about this, where ax equals lambda x. So this is the key piece that you guys are going to be working with when it comes to this problem specifically. So A says verify that A, B, and C are eigenvectors of A and find the corresponding eigenvalues. So we are going to plug in each vector to this equation where we have A times X, and then what should happen is it should appear as if it was just multiplied by a scalar. So A, write my A matrix. So the longest part about some of these problems is writing out, like literally writing the matrix a million times, but please make sure that you are showing your work. So when we do this, we have 0 plus 4a minus 4a, 0 minus 11a plus 13a, and then 0 plus 8a minus 10a. So notice what happens. We end up with 0, 2a, and negative 2a, which it appears as if we just multiplied our original vector by negative 2. Therefore, lambda a equals negative 2. Same thing for the next one. Two b, negative 2b. Multiplying this out, I get negative 6b minus 4b plus 8b. 14b plus 11b minus 26b. And then negative 10b minus 8b plus 20b. When I do that, I end up with negative 2b, negative b, and 2b. So it appears as if I've multiplied this vector by negative 1. Therefore, lambda b is negative 1. And then for my last one, same thing. My vector is c, negative 2c, and c. Multiplying this out, I get negative 3c plus 8c minus 4c, 7c minus 22c plus 13c, and then negative 5c plus 16c minus 10c. Adding all of those beauties together, I get negative c, positive c, it's positive, negative 2c, and then c. So it appears as if I multiplied the vector by 1. Therefore, lambda c equals 1. Woohoo! Okay, done. B, is matrix A diagonalizable? Yes. As an exclamation point. Because the eigenvalues are distinct. There are 3 different eigenvalues. There's no repeats. It's -2, -1, and 1. I have 1 and -1. That's fine. They're not the same. So I have 3 distinct eigenvalues. So therefore, matrix B is diagonalizable. And then it says C. Assume A, B, and C are 1, 2, and 3 respectively. So that means for all my eigenvalues, -2, my eigenvector is going to be 0, -1, 1. For lambda B, my eigenvector is -4, -2, and 4. And then for lambda C of 1, my eigenvector is going to be 3, -6, and 3. Find the diagonalization of A, showing all 4 matrices. So here's my 4 matrices. I already have A, I already can fill X, and I already know what lambda should look like. I just need to find the inverse. So A looks like A. X is going to be filled with my eigenvectors. So 0, -1, 1, -4, -2, 4, and then 3, -6, and 3. It doesn't matter the order that you fill them. They just become columns. So here's XA, XB, XC. When you fill in lambda, though, it needs to corresponds to this order. So if you have XA here, you need lambda A here. If you have XB here, you need lambda B here. If you have XC here, you need lambda C here. So that order matters. So lambda A, lambda B, lambda C. So A, B, C, A, B, C, or 1, 2, 3, 1, 2, 3. But it's always a diagonal matrix with your values along the diagonal. The last thing is we need to figure out what X inverse is. X inverse is literally just the inverse of X. So here it says use Gauss-Jordan elimination to find X inverse. So we are going to go ahead and do that one. I'm also going to do using the cofactors. So for finding the inverse using Gauss elimination, or Gauss-Jordan elimination, we end up with our A matrix, or our X matrix in this instance, placed next to identity. And then I just do Gauss-Jordan elimination. So first thing I'm going to do is swap rows 1 and row 2. Because I can't have a 0 there. It just doesn't work. Whatever I do to the right-hand side, I need to do, or whatever I do to the left-hand side, I need to do to the right-hand side. And now I can say that row 3 is going to be row 3 plus row 1. So row 3 ends up being 0, 2, -3, 0, 1, 1. Oops, that's supposed to be a negative. No. Ah, come on. Okay, no. It's supposed to be, there we go. It's supposed to be +4, 2, and -4. There we go. Just change the signs. Technically, either one would work, would give you the diagonalization because they're both eigenvectors. But we're going to go with what our problem statement says. Okay, so this is what we end up with. -2. There we go. Okay, so I've got my first column of zeros. Now I want my second column of zeros, so I want both of those to be 0. So I'm going to say row 1 equals 2 times row 1 minus row 2, and row 3 equals 2 times row 3 plus row 2. Once again, you would show your work. I am showing it just for the simplicity. I am not showing that just because there's a lot of writing and I don't want to take up too much time. So negative 2, 0, negative 15, negative 1, 2, 0. Row 2 stays the same. And row 3 becomes 0, 0, negative 3, 1, 2, 2. And then my last column of zeros, I'm going to say row 1 equals row 1 minus 5, row 3. And then row 2 equals row 2 plus row 3. And when I do that, I end up with all of my zeros where I want them. There we go. My last step is to divide this first row by negative 2, the second row by 4, and the third row by negative 3. When I do that, I'm going to end up with A inverse, or X inverse in this instance, as 3, 4, 5, whatever shows up over here. And then I get 1/2, 1/2, 1/2, and then negative 1/3, and negative 2/3, and negative 2/3. There we go. I found X inverse. So I can go ahead and copy these numbers and write them in my diagonalization. Paste. No! I'll paste them over here. There we go. Now I'll move them. There we go. I have my diagonalization. So that's one method we can use to find the inverse of x. We can also use our cofactors. So A inverse, or in this instance, X inverse, equals 1 over the determinant of x times x adjoint. So the determinant of x, you can use whatever method you want. I am going to do cofactor expansion along this first column here, so plus, minus, plus. So I have plus 0 minus negative 1 times 12 plus 12. And then plus 1 times the determinant of these ones, negative 24 minus 6. So the determinant of x ends up being 24 minus 30, or negative 6. Okay, so I need that number. It's got not 0, which it shouldn't be 0. If it was 0, that means you don't have distinct eigenvalues. Fun fact. And then I just need to find all my cofactors. So C11. So here's my grid, plus, minus, plus, plus, minus, minus, plus. So I have plus, and then 6 minus 24, which ends up being negative 18. C12 is going to be minus negative 3 plus 6, or negative 3. C13 ends up being plus 4 minus 2, or 2. C21 ends up being minus negative 12 plus 12. No. Right, okay. Yep, this grid here. This grid's confusing me, so I'll erase it. Now I have x gone. 0, 1, 4, negative 4. 3, yeah, okay, there we go. So C12, I'll draw my grid here. So I'm on this one. So negative 12 plus 12, equals negative 24. C2, 2 is a plus 0 minus 3, or negative 3. C2, 3 ends up being a minus 0 minus 4, or positive 4. C3, 1 ends up being a plus negative 24 minus 6, or negative 30. C3, 2 ends up being a minus 0 plus 3, or negative 3. And then C3, 3 ends up being a plus 0 plus 4, or 4. And then I can put everything together. So x inverse equals 1 over negative 6 times my adjoint matrix, where this here becomes my first column, negative 18, negative 3, 2. This becomes my second column, negative 24, negative 3, 4. And this becomes my third column, negative 30, negative 3, and 4. Then when I just multiply through, I end up with 3, 4, 5. 1/2, 1/2, 1/2, negative 1/3, negative 2/3, and negative 2/3, which is what we got with our Gauss Jordan elimination. There we go. That is problem 6. So there's a lot of pieces there. If I wanted to check my answers with MATLAB, it would look something like this. You could literally just plug in A. We have A directly. You could just say eig A. It will tell you all of your eigenvalues. So 1, -1, and -2, which we can check to make sure we got that right. Notice you could have done that without even solving A, B, and C, but you need to show your work. You need to show us that you know what you're doing. It is diagonalizable. The eigenvalues are distinct. You can't really check that in MATLAB. You just need to know that. And then we need our diagonalization. So you can plug in x. You can, whatever you got for x, you can find the inverse of x, and then you can show that inverse of x times a times x. That should give you your lambda. So you can check to make sure your inverse is correct. And then here we can see it really is lambda. This asterisk means it's practically 0. It's a really, really small number. So we can check and we can say, yep, it matches the order. It matches everything we got. So that is all of the practice exam problems. Make sure you go through those, go through the solutions, make sure you know how to do them, make sure you know how to follow the process. Show your process, show your work, because the process matters more than your final answer. Because if you make a minor mistake, you can still get most of the points because you're showing the process.